So these are, yeah, okay. So the next topic is the third law of thermodynamics. Okay. So before I give you the third law, well, actually, give you the third law and then we'll discuss its comparison with the other laws. So the second law of thermodynamics, so the second law tells us, how entropy changes, for isolated systems, right? And implicitly, for irreversible processes, it defines an arrow of time. So what we call time in our macroscopic world is determined by the second law of thermodynamics, or how entropy changes. Now, what the second law doesn't give us is what the absolute value of entropy is. And I think one of you asked this question, is that, can entropy be negative? Right? And I said, no, it can't be, because otherwise, it's something that counts the number of degrees of freedom, and something that counts something cannot be negative. So the third law basically tells us what the absolute scale of entropy is going to be. Okay. So the third law tells us, and it was discovered by many people, but I think most notably by Nernst. So it's also known as Nernst's law or Nernst Principle. And what it says is that if you take the limit of the temperature, and by this I mean the temperature of the thermodynamic temperature scale, which is known as Kelvin, then the entropy as a function of T goes to 0 in that limit. Okay. So this is the third law, and in fact, this can be relaxed a little bit. Systems may have finite entropy at absolute 0, but the entropy density, that is, if the system consists of n particles, then the entropy density must go to 0 as T goes to 0 and n goes to infinity. Which means that the entropy cannot, that at low temperature, entropy, cannot grow extensively. Okay, so this is the third law. Now, as David Tong says in his lecture, the third law doesn't have quite the bite as the second law, or even the first and the 0th law. And what he means is that, remember that the 0th law meant that there exists a state variable called temperature, right? And the first law means that there exists a state function, called internal energy. Okay, so this was a function of V and S. Well, it can be functions of other things too, but yeah. And the second law meant that there was a function of there was a state function called entropy, right? But the third law doesn't imply the existence of something like that. What the third law is telling us is that it's giving up what the scale of S is. So the third law has a very different character than the other laws. Another thing to note is that the third law is a 20th century law. So what does this mean? So this means that the third law actually, explicitly is inspired by quantum mechanics, whereas the other laws were empirical laws, okay? So all these are empirical laws that people, that people formulated without the benefit of understanding of the microscopic properties of matter. Of course, every physical law is empirical at the end of the day, right? I mean, Newton's law is also empirical. But what I mean is that the third law is, has the benefit of, knowing about the quantum nature or the microscopic nature of matter. Okay.